Okay, so we have to verify the correctness and construct the circuit. So let's start with the first example and design our own first sequential circuitry. It's a sequence detector where we have got one input and one output, and there's a clock. The problem specification is given as a design a circuit that detects an input sequence 101. So we have to detect 1, 0, and then 1 again in an incoming bit stream synchronized with a clock. So Z is going to be 1 in response to the last one in a sequence of 101. So that means it has to be, this is X, Z is going to be 1 when the sequence is completed, okay? So when this one is 1, when the clock is changing, we have got output as 1. This is what it's saying with the last one in the sequence. So let's see the input-output sequence. So 0, 0, 1 is not the sequence, so the outputs are 0, 0, 1, 1, it's 0, 1, 1, 0, it's 0, 1, 0, 1, the output is 1 over here. And then 0, 1, 1, it's 0, 1, 1, 1, 1, 1, 0, it's 0, 1, 0, 0, it's 0, 0, 0, 1, it's 0, 0, 1, 0, it's 0, and 1, 0, 1, it is 1 again. And then 0, 1, 0, it's 0, but 1, 0, 1 again, it's also 1, 0, 1, 0, it's 0, and 1, 0, 0, it's 0. So we are taking each of these bits as a sequence and find out where output is going to be 1. Now, the question comes in, is this a milli machine or Moore machine? The question is this a milli machine or Moore machine? How do we understand? Now, what we can see from here, the output is not waiting for the clock. Output is just waiting for the input X. Whenever the input X is changing, output is changing. So what do we know about the milli machines? When the present state and the input is affecting the output, it's a milli machine. Moore machine, it's only affecting from the present state. So that means this is a milli machine. Okay? So we can say that the type of machine that we are seeing in this description or the problem, it's a milli machine. Now, we have to design a state graph. So we have to keep the track of the states, and we should know how to jump from one state to the another and what will be the conditions over there. Okay, so let's go back to the description. Let's stay over here and start with the first state. Let's say the first state is S0. We know that it's a milli machine, so the outputs are going to be written with the inputs. So if the input is 0, I just need to wait over here because I cannot go for the next state because I'm looking for 101 pattern. So when there is a 1, I have to go to a new state and expect something else. Otherwise, I'll wait over here. Then S1. So if state, when we are in S0, if the input is 1, that means I'm satisfying the first bit of the pattern, so I can go to the next state. While I'm here, the outputs are 0. Okay, so nothing is going on at the moment. Okay, so when we are in S1, because we have received the first input as 1, if the input is 0, that means I have to go to another state, because 0 is also the part of the pattern. Okay, so that means I can jump to a new state. So whenever I get the right bit for the input, I can jump to the next state. While I'm here, am I satisfying 101 pattern? Not yet. so that means output will be 0 as well. So how about if when we are in state S1, if the input is 0? Now, if the input is 0, that means the pattern will be like 1, 0, 0. Is this what we are looking for? It is not. Sorry, when it is 1, sorry, not 1, 0. When it is 1, 1. Okay? So because 0 jumps to the S2, 1, it's going to be another 1, so I can wait over here. I don't need to go anywhere else. I can wait over here for another 0 so that I can jump to S2. So it can be like 1, 1, 0, then I can jump to S2 because this is still satisfying the first 2 bits of my detector. Then, when we are in S2, if the input is 0, now when we are in S2 and if the input is 0, now this is breaking the sequence because 1, 0, 0. It's going to be 0, 0. That is breaking the sequence. This is not what we are looking for. We are looking for 1, 0, 1. So at this point, I have to go back and start again. Again, the output is not satisfied, so I have to put there over 0. Now, when we have got S2 and the input is 1, where do I need to go? This is the tricky point because we are going to get 1, 0, 1 pattern when when we are in state S2 and the input is 1. But after that, what will happen? So output will be 1 over here when this is X and this is Z. Okay, and if I got another 1 afterwards, that means I can get into this loop and I can stay over there. Okay, I can have some kind of a loop over there. Then if it's another 0 and then another 1, I can satisfy it and I can have another 1. So I can reuse these in between ones again if I return back to S1. So that means it's better to have it this way, and I'll put it over there. So input is 1, then output is 1 over there. So all of my sequences 1, 0, 1 are all satisfied, confirmed. That means it will be enough to implement this circuitry. Okay, so this is how we can get into this sequential circuit design by deriving the relationship between the states and the inputs. And we also have the outputs over here. Now, as you can see, I have used S1, S2, and S0. Now I have to do a state assignment. Okay, so let's go step by step from here. Now we know that it's a milli machine. We have to derive a state graph. So start with the initial state 0. Check if the input is 0. No, if it is 0, not interesting. We have to wait until we get the first interesting bit to come in. When it is 1, I jump to the next state. Output still 0 on that point. First bit of the sequence is detected. Then when I'm in 1, 1, 1, still interested, we might have a sequence, so I can wait over here. And then 0, okay, I have got the second bit detected, so I can jump to a new state. And then if it is 0 again, that means the sequence is broken. I have to return back. If it is 1, I can keep it over there because it's going to be a 1 and I can expect a new 1 and I can carry on. Okay, so that's why we are returning to S1. So we are done with the second state, which is the state graph. The third one is the state table. Now, in order to derive the state table, I have to do a binary assignment. Maybe we can do it without a binary assignment. Let's derive the state table first then. So we have got states, okay, and we have got S0, S1, and S2. On the other side, I have got S plus. S plus when x is equals 0, when x is equals 1. I can do a two-dimensional table. And I also have, this is like ST, not S plus now. And I also have the output Z, which is where x is equals 0 and x is equals 1. So three states that I can have and the possibilities. Now, if I look at it and get the information from the state diagram, when S is 0, input is 0, the next state is S0, input is 1, next state is S1. And on both points, outputs are 0. Then, when we are in S1, if the input is 0, it goes to S2. If the input is 1, it waits there. You can see it from here. And the outputs are still 0, 0. And then when we are in S2, if the input is 0, I go back to S0. If the input is 1, I go back to S1. And I know that when input is 0, it will be 0. Otherwise, it will be 1. So this is how I can get my state table. As we have got the state table, we can check if we can eliminate any of the states. Eliminating means we're getting rid of it. They have to have similar inputs and similar outputs and similar next states. Do we have any over here in this simple state table? I'm afraid not. So we cannot use any of these. We cannot get rid of any of these. Then the last thing that we are going to do is state table with the binary assignment. Okay, so we have to assign binary values for each of these. S0, I'm just going to use ordinary binary. S0 will be 0, 0. S1 will be 0, 1. S2 will be 1, 0. Now, you might ask, how many flip-flops we will require over here? As we have got three states, and we cannot get rid of it, we need to have at least two flip-flops to cover four possible states. And as we have used all three, 1, 1 will be unused state. Okay? So we can say that it's XX. It's unused. Okay, so in this case, what we need to do is we are going to redraw our state table. So S again, S plus, and Z when x is equals 0, when x is equals 1, x is equals 0, x is equals 1. So state 0, it's going to be 0, 0, 0, 1, and 1, 0. Three states again. And I just need to replace the letters with the numbers. So if we look at over here, when we are in S0, if the input is 0, next state is 0. And if the input is 1, next state is 0, 1. So I can fill it 0, 0, and 0, 1. Outputs are 0. When we are in state 1, if the input is 0, then we go to S2, which is 1, 0. If the input is 1, it's going to be 0, 1. So 1, 0, 0, 1, and the outputs are still 0. And the last one, so S2, if the input is 0, it goes back to S0. If the input is 1, it goes back to S1. And then 0, 0, and 0, 1. And that's it. So that's all we need to do. I just need to write the outputs over here as well. And I have got the state table with the binary assignments completed. Now, we have got almost everything that is required. We have got state assignments and the flip-flops. We need two flip-flops. It's obvious. If you want, you can write it as like that as well. So A, B, and X, and then A plus, B plus, and Z, and you can create your table like that as well. That is also possible. Okay, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This is also possible. Either that one or this one, doesn't matter which one is better for you or suitable or easier. You can use that one. So what do we have? When present state is 0, 0, if the input is 0, we stay at 0, 0, and it's 0. Then it is 0, 1, and it is 0. So that's done. That's done. 0, 1, 0, it's 1, 0, and the output is 0, 0, 1, 1. It's 0, 1, and the output is 0. 1, 0, input is 0, then 0, 0. 1, 0, input is 1, then it's 0, 1, and then 1. And these are unused states, so we can just put don't cares. Now I have got all the information required. Now, as it didn't say anything specifically what type of flip-flop we need to use, we can use D type, which will be the easiest one. So what do we know about D type? Once again, Q next is equals D. Or in this case, A plus will be equal A. Now, if we look at it, that means if I extract the information over here in these two columns by using K-maps, I am also going to get the input for my flip-flop. Okay, so let's put those down to the K-map. I need two K-maps with 3 inputs. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, and ABX, ABX. Then I just need to put all those in. Let's say this is for A plus and this is for B plus. Okay, so 0, 0, 1, 0. 0, 0, 1, 0. Then 0, 0, x, x. So 4 is 0, 5 is 0, 6 is x, 7 is x. Now I can combine these two, which is going to give me bx prime. So I can say that A plus is just bx prime. So dA is also bx prime, as D-type flip-flop is just the D is equals A next state is D. Then I repeat the same thing for B, 0, 1, 0, 1, 0, 1, 0, 1. And then we have got 0, 1, x, x. So 0, 1, x, x. And on this one, I can have center 4, which is going to give me x. So I can say that b plus is equals x. And in this case, db is equals x. So I have got two flip-flop input equations. All I need to do is implement it. So I need two flip-flops, D-type flip-flops, D clock, Q, Q bar, Q bar. Right, so DA, let's say this is A, this is B. DA is BX prime. B is flip-flop B. X prime is just inverted version of X, which is feeding in to D. And DB is just X, so I can just get that one and connect it directly. And the clocks are connected. Now, one thing that we are missing now is the output. Because we have got this output from here, I can create a K-map for that output as well, which is just the combination of those. Okay, now maybe I don't have space over here, but I can create it over here for X, for Z, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and then this is A, B, X again. So all of them are 0. So 5, 6, 5 is 1, 6 is X, 7 is X. So these are all zeros. 4 is 0, 5 is 1, 6 is X, 7 is X. So I can combine only these two, 5 and 7, which is going to be A and X. In this case, I can use Z equals A and X, and on my diagram, it's just A and X, so I can have the output an AND gate, which is feeding from A, maybe a little bit further, feeding from A and X. This is Z. That's it. We have got the sequential design using D-type flip-flops, which we have implemented a sequence detector. Now you can try by yourself, you can go through by yourself to see if you're going to get the same implementation. You'll see that you are going to get these input equations, which you can just plot them using D-type flip-flops.